Welcome back. We're now with lecture 15, the second part for chapter 10. And we're going to look at source transformations and then Norton and Thevenin circuits. Again, we're just going to work through quite 1, 2, 3. I'm going to try and work through 4. Oh, goody gumdrops. I'm going to try and work through 4 problems, so it's going to go a bit quicker. You've got the video, so if you miss something, just roll back and follow that. So we're going to start with source transformation first. Now, perhaps just a word on source transformation. Source transformation is for me in the same category as resistors in series and parallel. So the objective of using source transformations, in other words, converting a voltage source in series with an impedance into a current source parallel with that impedance, like we did in the previous example in the previous lecture, or you can vice versa, is so that you can simplify your circuit to a point where you can get the variable that you want. So in practice problem 10.7 behind me, we want that output current. So what our objective is going to be is to simplify the circuit as far as possible to the point where you can either just quickly do a voltage division or a current division to get that final current. So we're starting with a current source parallel with an impedance. Now all we're going to do now is redraw the circuits. We're not going to calculate anything yet. We're just going to redraw. So if we simplify the circuit, we're going to do a source transformation with these two. That will convert my circuit into a plus minus resistor capacitor. So now we're working with those two terminals, to the left of those two terminals. So there are those two terminals. The rest of the circuit obviously then stays the same. Okay, and then the output. Okay. Now, if you've got the circuit in this position, hey, now we can see, wait a minute, we can combine all of that in series. Okay, so our next simplification would take my circuit to something that looks like, well, there's now 2 resistors there, which will become 1 resistor. What is going to win? This is the combination of the cap and the inductor now going to be a cap or inductor. Well, I've got minus J3 and I've got a plus J1. So I'm going to get minus J3 plus J1. So it's going to end up to be a capacitor minus J2. So I'm going to draw that as a capacitor. So now I'm simplifying between those two terminals. So then I am left with a circuit, still the inductor, and then still that resistor and that capacitor. Okay, but I'm still not, I want the current in that leg. Can't I then go one step further? Again, we're going to take this now to the extreme. So let's go from here to there. Let's do another source transformation with those two. So I'm going to get a current source pointing upwards. Why is it pointing upwards? Because my positive terminal is at the top. And then that is going to be parallel with that resistor and that capacitor, which is parallel to that inductor, which is parallel to the branch that I actually want to get to. Ooh, now we're getting too close to a current division, but I still need to combine those two. So one last simplification we would have to do is to keep my current source in there, and now we're going to get that parallel combination. So let's just call it for now that doesn't even nearly look like an arrow, does it? That's better. So let's call that LZ parallel, and then we still have our original circuit with the I out that we're looking for. And then we're going to do a current division. Now when you get to this point, you've solved the entire problem without punching anything into the calculator. You see, it's the methodology that's important, not the number crunching. Yes, the only way I can test your methodology is through the number crunching. So how is this going to be tested in the test and the exams? I will give you this circuit. Next thing I'm going to give you is this circuit. And then I'm going to give you this circuit. And I'm going to ask you to calculate that value for me and the new impedance. And I'm going to ask you, well, now you got from this circuit and you simplify to this one. So I'm going to test whether you're able to see how did I get from this to this and how did I get from this to this. And you need to fill in the gaps, do the calculations to get these parameter values. So let's quickly run through that. So what is this value going to be? Well, I need to take that current, which is a that's 2.4 by the way. So this is 2.4 angle 90 degrees multiplied with the 4 minus J3. So this gives me how much? 12. 5 times 2.4 is 12. No, yes. All right, so that gives me 12 angle 53.13. There's a 0.13 degrees volts. Okay, so I've got that one. These impedances are still the same. It's still the 4 and the minus J3. Right, now I combine the 4 and the minus J3 with the 2 and the 1, so that means I get a 6 over here, and as we mentioned a little bit earlier, a minus J2 there. That still stays the same, and this voltage source, am I still going to, yeah, that's still the 12 angle 53. Now let's just write that, 12 angle 53.13 degrees volts. Now we need to go from this to this one. So how are we going to calculate that current source? Now let's call it IS over there. So what is my IS? Now I'm going from a Thevenin equivalent, which is a voltage and a series impedance, back to the current. So now I need to use this impedance and I divide. So it's going to be my 12.5, I want to say 12.53 the whole time. 12 angle 53.13 volts. Then divide by the impedance, the 6 minus J2. And that current is, I don't have enough space there. That current works out to be a 1.9 angle 71. Let's make it 57 degrees amps. Okay, it's actually 565. So keep the more digits you can keep, the better, of course, for accuracy. But I'm running out of space. So I've got IS. This impedance now is 6 and the minus J2. This one is still a J5. This is still 1 and minus J2. Now for Z parallel, so that's now going to be the 6 minus J2 parallel with the J5. And you get a 3.333333 plus J3.333333. That's interesting. 3.333 plus J3.3333 ohms. Okay, so I've got IS, I've got Z parallel. Now I can go and calculate I out somewhere where I don't have any space left. So let me just do it at the bottom here. And you would now do it below. Okay, so now we can say I out equals this IS multiplied with what? The IS splits between the two. So I want I out, so I need to put the Z parallel at the top. Z parallel over Z parallel plus 1 plus, there we go, 1 minus J2. Okay, so did I write it? I probably wrote it out here. So let's be nice. So my IS, did I just wipe my IS value? No, it's there. Then 1.9. 1.9 angle 71.57 degrees. multiplied Z parallel, yeah, 3.3 plus J 3.3 repetitive over 3.3 repetitive plus J 3.3 repetitive plus then that branch, which is the 1 minus J2, 1 minus J2. Right, so there you've got the whole expression. Yeah, you can actually do it like this, because it's a multiplication. I can actually just pull that whole line through. And that then equals the final answer that you're going to get. Where's my faithful chair? So that I can write nice and neat. You're going to get a current of 1.97 angle 99.46 degrees amps. Ugh. Alright, so there you got it. That was just the chair that fell over. Or something else. Right. There's my final answer for I out that I'm looking for. So why I like this method so much, it's a very graphical method of solving your circuit. So I like this method a lot. You graphically simplify your whole thing, and then somewhere on the circuit diagrams where you've simplified, already solved the problems, you then quickly do your number crunching so that you can get to the final answer. Okay, so that is practice problem 10.7. We're now going to look at Norton and Thevenin equivalence. Now, I know you guys have this phobia or this mental block against it, but hopefully I'll be able to remove that for you. What is a Thevenin equivalent circuit? It's a voltage source in series with an impedance. And Norton is a source transformation of the Thevenin equivalent, and vice versa. So if you have the Thevenin, you have the Norton. If you have the Norton, you have the Thevenin. It's just a source transformation away. And how do you get to the Thevenin and Norton circuit? You just use circuit analysis to find a specific voltage, impedance, or current. So now they want, in practice problem 10.8, they want the Thevenin equivalent impedance. Yes, the Thevenin equivalent between terminals A and B. Now, for some reason, the textbook always loves to put that impedance or those two terminals at a weird and stupid place. So all I'm going to do is I'm going to put it at a place that's more normal, and I'm going to shift those two to the side. So I'm going to redraw my circuit that it actually fits my fancy a little bit better. Fancy a bit better. Terminals A, B. And when I want to calculate the Thevenin equivalent, what am I going to do? I'm going to look in between these terminals, and I want to know the following. If I were to take my multimeter and I measure across A and B, what is the voltage going to be? That's your Thevenin voltage. All right. If I want the Thevenin equivalent impedance, and that you did over and over again in EVN, is what is the impedance that I see when I look into terminals A and B? How do you do that? You make all the independent sources zero. The independent sources. We're going to do an example just now where there is a dependent source in the circuit, because that's usually where the wheels come off. Okay, so let's do the Thevenin impedance first. So for that, you have to take your voltage source, and it's going to become a short circuit. For the sake of space, I'm not going to redraw my circuit now. All right. So that then becomes 0 volts. What do you see when you're looking in this? So now I need to simplify from that direction. So the 6 plus J2, obviously in series. That combination is in parallel with a capacitor, which then will be in series with a resistor. So let's write that down. So my Z Thevenin equals the 6 plus J2, which is parallel with the minus J4, which is in series with, oh dear, I didn't even bother writing a value for that. It's 10 plus 10 equals. If you can't see that, this is how they're connected, go and redraw the circuits. All right, but you need to be able to at least for a simple circuit like this, see that these two are in parallel, and once they're in parallel, well, what's your circuit going to look like then? Let's just draw that. When you have the parallel combination, and then you're going to have the 10 ohms, that's what you're left with. There's Z, there's your Z parallel, then everything is in series. Alright, so you need to be save time and be able to visualize that. But of course, if you're not sure, rather draw it out. Okay, that impedance then gives you a 12.4 minus J 3.2. So it's still a capacitive, dominantly capacitive load. Okay, for Thevenin, you have to put your source back in. Right, so there's our source. And now I want to know what voltage am I going to measure there. Let's start to get to know the circuit. There's the source. The current will start flowing. Oh, T-junction. Where is it going to go? How much current is going to go down? How much is going to go to the right? Everything has to go down. Why? Big hole, big problem. So you can't have any current flowing through that. So all of the current comes down through the cap and then gets to this point again. But wait a minute, there's no current flowing through the open circuit, so no current through the 10 ohms. So you actually just have this one loop where current is flowing. Okay. So if there's no current flowing through this 10 ohms, what's the voltage drop across it? Nothing. No current, no voltage. So no voltage drop across that. So voltage VAB, which is now your Thevenin voltage, I should have actually written it the other way around. Mathematically, it should actually be that your V Thevenin equals VAB. That voltage will then have to be the capacitor voltage because there's no voltage across that. Or if you want to write a KVL, plus minus, it will be the voltage across the cap plus the voltage across VAB plus the voltage across the 10 ohms must equal 0. But you're going to have a voltage plus 0 equals 0. So this voltage just falls away anyway if you write out your KVL. So you've got V Thevenin equals VAB equals the source voltage. You know what, let's just write the values because they don't have names. So it's going to be the 75 angle 20 degrees multiply minus J4 over minus J4 plus that impedance, which is the 6 plus J2, and you will get a 47.43 angle minus 51.56 degrees volts. Okay, you've just done your first Thevenin circuit. But yeah, it doesn't really get in any easier than this. What did I do here? Oh, I did source transformation. Ooh. Yeah, so I actually went, you can solve this whole thing and get to Thevenin with a source transformation. So what do I mean with that? Take this voltage source and impedance, make it a current source parallel with the capacitor and the new impedance. Combine the two parallel impedances and then convert that with a current source that you've created into a new voltage source, into a new source, and then you can simplify this whole thing to a much easier circuit to solve. Alright, so you could have done it that way as well. That is practice problem 10.8. Let's go to the next one. Practice problem 10.8. So let's look at our circuit diagram first. Again, we need to probably give terminal names there. AB, we want to determine the Thevenin equivalent between terminals A and B. Now, when you get to a question like this in a test and exam, you look at the circuit diagram, you see a dependent source, and it's a voltage-dependent current source, and then you go in your head, let's try the next question. Let's skip this one. No. It's just a little formula or little recipe that you need to follow to solve these circuits. Yes, it's definitely a bit of schlep in terms of time and effort, but it's not undoable. Okay, so let's just get to know the circuit. So we always worry about this one first, and we see that this current is dependent on V out. Where's V out? There it is, plus minus. So if I know the voltage across that impedance, which is also the voltage then across this current source, I will know what that current is. Okay, then quite a difficult one. Current source coming in. Where's this current going to go? So you've got current coming in, you've got current coming in. So I'm assuming the current will go that way. But now they're stupid because they gave a plus minus, though I suspect that the current will be going in the opposite side of the polarity. But that's okay. The math will sort it out. And then I've got the capacitor resistor over here that seems to be hanging there around doing nothing. Okay. First, let's get the Thevenin equivalent impedance. So looking into AB, what is the equivalent impedance that I see? What's the rule? You have to zero all the independent sources. There's only this one independent source, so let's make that one 0. What happens when a current source becomes 0? It becomes a open circuit. Okay. Open circuit. There we go. That's the first thing. Next thing, because there is now a dependent source in my circuit, we have to go and put that A and B is a bit in the way. Let's just make it like this. And this is the hardest part for Thevenin equivalent circuits when you've got a dependent source, is we know that we now need to go and put our own dependent source in there. It can either be a voltage or a current. We're going to make it 1 volts or 1 amp. But we don't, which one is the best in this case? Should we put a current source or a voltage source? Is there a right and a wrong? No. Both of them will have to work, but there's always a better one. And then if you put a voltage source, plus at the bottom or plus at the top. And if it's a current source, we're going to make it point upwards or we're going to make it point downwards. Okay, so let's see what the circuit does without this one. If there's a source, it'll push a current into that node. If it pushes a current into that node, then the current will now flow that way and downwards. So because it's going to push this one will push the current downwards. Let's choose a current source going down. Why not put a voltage source there? Well, oh yeah, now I remember from previous years, it's actually better to put a voltage source down there. We'll do both. Okay. So if you put a current source there, we know we're going to make it 1 amp. What's our objective? Why do we have to current source in there? Because Z Thevenin is now going to be this I out, Ohm's law, is going to be the voltage divided by the current. So I still, wait, it's going down, yeah, so it's plus minus. No, other way around, sorry. That way, it's a source. In a source, it goes from minus to a plus. So this is going to be my, what did I call it? Because I can't call it VS. Okay, so this is IS now, and this is VS. So that V Thevenin is VS divided by IS. That's always the case. Sometimes we choose it as a voltage source in there, sometimes we choose a current source in there. Now we've chosen it to be 1 amp. So in order to solve for V Thevenin, I now need to go and determine what the voltage across those two terminals is. So what is that voltage? Well, it means if you look at these terminals, everything there is the same terminal. All of this, same terminal. So if I can figure out the current flowing through this leg, through this branch, I will have to find the current through this branch so that I can get the voltage across this branch, which will then be the voltage that I'm looking for there. Okay, so let's go and look at what the current is doing. So this current, I just want to keep to what I did in my notes. Yeah. You know what? I'll get there anyway. I don't actually like my notes on this one. Okay, I've got current going into this node, current going out. So let's do a KCL. Now I'm going to, because this one is a plus and minus in that direction, let's define a current flowing through that resistor, and we're going to make this I out because it's V out, so I'm going to make it I out. And I'm making it go in this direction because I've got a positive negative. So that current is the current that's flowing in this whole branch. And if I know this current, I can calculate V out. And once I've got, I've got the voltage across this impedance, so I've got the voltage across the total impedance, which is then Vs. Okay, so can I solve for I out? So let's write down a KCL at that node. All the currents coming in must equal all the currents going out. So just a normal KCL. So what are the currents coming into that node? I out is coming in plus 0.2 V out is coming in, and then my IS is going out. So that must equal IS. So that's just the equation at that node. IS, we know what that is. I out is the one that I'm looking for. So can I get rid of V out and write V out as a function of I out? Yes, you can. Because, wait a minute, so let's write here, but V out is simply I out times the 8 plus J4. 8 plus J4. Okay, so in other words, I out plus 0.2, 8 plus J4, I out must equal 1. So if we multiply this out, I out plus 1.6 plus 0.8, there needs to be a J, I out equals 1. So you've got 1 plus 1, so 2.6 plus, I need a bracket there, sorry. Bracket's important. Plus J 0.8 I out must equal 1. Like that. Which means I out is going to be go away, 0.3676 angle minus 17.10 03 degrees amps for the current. Okay, why do I need I out? So Vs, so let's just go back to this one. Remember, the actually thing that I know this, I need to know what Vs is. Now Vs plus minus, remember you've got IO going all the way up here, so it's going to be equal to I out times that total impedance. So the 4 minus J2 plus 8 plus J4. So this is I out times 12 plus J2. So then I've got my Vs. So now you can see actually I actually don't need to know what where's my IS over here. My IS is over here. I'm going to keep this IS. So now if I divide Vs, I need to divide Vs by IS. So if I now simply take this and divide it by that value, the I outs are going to cancel. Let me just get rid of this one. So what am I saying? So remember now that you've got, oopsie, let me just show you what I mean. So Z Thevenin equals, what is Vs? Vs is this, the 12 plus J4 times I out. Divide by IS. What is IS? IS is 2.6 plus J 0.8 I out. So for I outs actually cancel out in the end, which means you didn't really have to go and calculate it. And then you're going to get a 4.43 minus J 0.4 595 ohms. All right. So there's your Z Thevenin. What if we put a voltage source in there? Let's quickly look at that scenario. So what if instead of a current source? Now, the same principle is going to apply. That's still my plus. Let's take this out because I don't know what I'm going to put in there. I still want a Vs over Is. Now, how am I going to get, if I'm going to put a voltage source in there, then you would have to go and calculate the current that flows through there. What will the current be that flows through there? Well, you're going to have this current coming in, and there's this I out that's going to come in as well. So with this voltage given there, and that's this current coming in, you know, let's make our Is now in that direction, and we put a plus. No. If the current is going to come down like this because of the I out and this current, then you need a plus minus in that direction. This is now going to be your Vs, and we're going to choose this now to be 1 volt. So now we've got this. Okay, now I don't have those calculations, so let me just put this down. So now I need to calculate what the current is. Note that this is now a source, so don't get confused with the current going from positive to negative. In a source, an independent source, the current goes from the negative to the positive side. So now again we need to figure out Is, so let's write again a KCL at that node. What are the currents coming in? Currents coming in is I out plus 0.2 V out must now equal Is. So same story, but V out equals I out times this 8 plus J4. So that stays, that's important. So I can get rid of the V out and substitute it with I out, or you can get rid of I out and substitute it with something V out. Which one would be the better to do? Now this is where getting to know your circuit is now important. I've got Vs over there, 1 volt. 1 volt. 1 volt. It's 1 volt across this whole bit with a positive at the bottom, negative on that side. Can you calculate I out? Yes, you can. If I have I out, I have V out, which means I will have Vs. Okay, so I out is Vs divided by this total impedance. And now note the polarity. I've got the positive at the bottom node, the negative at the top node. So this source connected across this impedance is going to push the current in that direction, which is what I want because I've got plus minus I out, and I've chosen this I out to be in that direction. So everything works out nice. It's going to be Vs over this 4 plus 8 plus, well, minus J2 plus J4. So it's 1 over, because I chose it to be 1 volts, over 12 plus J2 equals something. I don't know. That means I've got I out. If I've got I out, I substitute this value, can then go into that term so that I can get 0.2 V out. The combination gives me Is, and Is goes into this equation, and you get 1 over Is, and you get your Thevenin impedance. Alright, so I didn't do the number crunching. I'm not going to spend the time now. Go through that exercise. Obviously, you have to get the same Z Thevenin value. Alright, so that is practice problem 10.11. Whoopsie, that wasn't practice problem 10.8. This is actually practice problem 10.9. Oops. 10.9. A bit late, but anyway. Okay, I once heard the professor when I said, yeah, it's only a little rather late than what? Rather late than never. And then he said, yeah, but rather never late. So I never got that one. That was a Prof. Malherbe. You won't know him. But yeah, that rather never late than rather late than never. Okay. We're not done with practice problem 10.9 yet. I thought we were done, but we're not, because we've only calculated Z Thevenin so far. We have not yet calculated what do they want? The Norton, the Thevenin equivalent voltage for this circuit. So now for the Thevenin equivalent voltage, we have to put back our source, angle 0 degrees amps, and now for the open circuit voltage, that's your Thevenin voltage. So I now need to go and determine what is voltage VAB. So yeah, just getting the Thevenin equivalent impedance is a heck of a lot of work. Now we can go and get the Thevenin equivalent voltage, Thevenin voltage. So what is the voltage at that point? And this is now where there's always more than one way to get rid of this now, or to solve it, not to get rid of the problem. I'm going to do it in two ways. I'm going to show you two different ways. The first one is just using KVL and KCL, just fundamental tools. So that comes with a bit more experience. But then you can also solve this now with any of the other techniques, nodal analysis, mesh analysis, all those type of things. So let's just do it with basics first. You know what? Let's rather stick to... No, I'm going to stick with the basics because it's much quicker actually. I just looked at the nodal analysis method. I'll show you, but let's just do a basic. I want the voltage across these two terminals, okay, which is the same as the voltage as what we did reasoned the voltage across these 2 points. So if I can find this current and calculate the voltage drops across, if I can get V out and this voltage, I'm going to have VAB. So let's call this one, I probably gave it a name, V2. So what I'm reasoning here is that V Thevenin equals VAB, which is going to be V2 plus V out. So to get V2 and to get V out, I need the current there and I need the current through that point. Okay. So, well, if it's a plus and minus in that direction, I probably have to choose this current to go down, eh? Because I've now chosen the polarity like this. So you're going to have a current going down, and we'll have to call it I2 because I called it V2. Okay. So KCL at that point I could do, wait a minute. And this is where the aha moment comes in. Current flows down, comes through this node, gets to this point. Where does it go now? Only up. Can only go up. Open circuit, can't flow there. So, I2 is 2VO. I2 equals 2VO. But VO equals I out times 8 plus J4. So this is 2 times V out is I out, the 8 plus J4 times I out. Okay. So I can write I2 as a function of I out. And this 2VO I can also write in terms of I out. So let's do a KCL somewhere at that point. Okay. I don't know what I did there. I'm going off my notes now. If I write to KCL there, all the currents coming in must all equal all the currents going out. So all the currents coming in is 8. Angle 0 degrees, so I'm just going to, let's write 8 angle 0 degrees. Plus I out. Plus 0, that's a 0.2. Sorry, not a 2. That's a 0.2 there. 0.2, 0.2, plus 0.2. V out is coming in. Okay, and that must equal 0. Okay. But I know what V out is. V out I can write in terms of I out. So let's say but V out equals I out times that 8 plus J4. So we've got that 8 plus I out plus this story, the 0.2, 0.2, 8 plus J4, I out must equal 0. So in other words, you've got that, let's multiply 0.2 times the 8 gives me a 1.6 plus this gives me 2.6 and then plus J 2 is 8, 0.8 I out must equal minus 8 because that 8 goes over. And I probably got that one somewhere. I out. No, I didn't. Okay. So that gives me an I out equal to 2.941 angle 162.2. Make it 9 degrees amps. Okay. So that's this I out. Now back to this equation. So what is V2? V2 is I2. Let's just write this. I2 times I2 times 4 minus J2 plus what is V out? V out is I out times 8 plus J4. 8 plus J4. But we already saw that I2 we can write in terms of I out. So this then becomes 0.2, the 8 plus J4, 8 plus, oh dearie me, 8 plus J4, I out. Alright, so now we've substituted that I2 with all of this, and this we still need to multiply with a 4 minus J2, and then plus that I out 8 plus J4. So we've got a 8 plus J4 I out, 8 plus J4 I out. So we're going to write this as, and we know what, no, let's just write this, I0 times 8 plus J4. And then we've taken this out of this equation. So 0.2 4 minus J2 plus 1. Okay. And I out we have, it's this one. And we plug that in there. And if you plug that in and then you work out, do all the number crunching, you will get a voltage of 11.76 angle 72.9 degrees volts. Right, there you go. Okay, 11.76 angle 72.9 degree volts. Okay, so this method, this method really needs you to get to know your circuit. Use basic KCL, KVL. So this was a KVL that we applied there. Then we did the KCL to calculate I out, and then we started substituting it all back. So you could get lost in this method. And if I just look at what I did over here, it seems I did it a different method on this one. So how would you, in a more perhaps systematic way, solve for this? Now having the tools of nodal analysis, mesh analysis, and all that. Oh dear, that one got wet. There's a piece of chalk. Okay, so let's use a nodal analysis to do this. So rewind. So the method that I showed you, now that might be confusing. You could get lost. And perhaps now when I'm going to do the nodal analysis, even though it's going to be a bit longer, you'll see that your chances of getting lost is a lot smaller. Okay, so we've already got this as V2. So let's now call this V1, which is our Thevenin voltage. So remember, our objective still is to solve for the Thevenin voltage. In this case, we've got that V Thevenin is now going to be equal to V1. So now we're going to use node voltage analysis. Now, why node voltage analysis and not mesh analysis? Remember, node voltage analysis, voltage node and node, uses KCLs, currents coming in, currents coming out. And here I've got currents coming in, currents coming out. So node voltage analysis might just work lacquer. Now, we don't need to solve for V2 this time. We only need to solve for V1, but it's still two unknowns. So we're going to still have to write down two equations. So let's go node 1. Remember, all the currents going out if you're doing nodal analysis. So I'm choosing that direction, and that direction. This I out actually at this stage does not exist for this exercise, so let's just take this one out. Okay, so node 1, all the currents going out. Let's start with this one. So I've got minus 0.2 V out. I've got minus 8. I'm going to dispense with the 0 degrees because it doesn't make any difference. And then I've got plus. So both of these are minus because they're pointing into this node. And then I've got V1 minus V2 over 8 plus J4. 8 plus J4. Now this V out is a bit of a bother, hey, because I've got 3 unknowns. So can't we replace V out with something V1-ish and V2-ish? Okay, this needs to be 0. So V out is across this. So, okay, wait a minute. We can write V out. But V out equals now positive on this side. So it's V2 minus V1. So it's V2 minus V1. So let's substitute that back into this equation. So I get minus 0.2 V2 minus V1 minus 8 plus V1 minus V2 over 8 plus J4 equals 0. Now what am I going to multiply with? I probably just multiplied everything with that 8 plus J4, didn't I? Where am I now? Oh yeah. So now let's get all the V1s and the V2s together. Okay, so for V1s, I've got a minus 0.2 times a minus over there. So I've got a 0.2. Nothing there. There I've got a plus 1 over 8 plus J4. That's all the V1s. The V2s plus, I've got a minus 0.2 there, minus 0.2, and I've got another minus over that, so minus 1 over 8 plus J4 V2. So that minus can become a plus, and that can become a plus if we make this a minus. And all of that needs to equal 8. All right, so is that what I did over here as well? Yes. Okay, so this is my equation 1. All right, obviously you can go in and simplify those two terms. I see that I did not do that. Okay, so I get something V1 and something V2. I don't know why I didn't do it, but either way. Okay, Then let's go to, how much space am I going to need for node 2? Oh bother. Okay, for node 2, this one. All the currents going out. So now I've got that current, I've got this current, and I've got that one going down. So let's start with the top one. V2 minus V1 over that 8 plus J4. 8 plus J4 plus that one, which is an 8, plus this one, which is now V2 over, oh yeah, sorry, this is now my reference node. I'm using nodal analysis. I'm using this as my reference node, so it becomes V2 over this 4 minus J2. 4 minus J2 equals 0. So now I'm just going to get all the V1s and all the V2s together. So there's only this one V1 now. So I'm getting a minus 1 over, there's a minus 8 plus J4 V1. Right. Then for the V2s, there's that one, 8 over J4, and there is just this one. What happened to, oh yeah, that's another equation. Alright, so then plus, I've got 1 over 8 plus J4 plus 1 over 4 minus J2. All of that times V2 must equal minus 8. So I just need to keep my varkies together. Yes, there we go. Okay, now I did not use the determinant method in this case. I just used substitution. So this is my equation number 2 there. I'm looking for V1. So one of these equations, and I think I took this one, I said, all right, since I'm looking for V1, I'm going to write V2 equals something. So I simplified this. Yeah, it really makes it really difficult not having the space at the bottom here. No, let's not do that. I'm just going to rewrite equation 2. So let's just say from 2, okay, in your case, so now I need to keep all my varkies together. I'm going to simplify that one. If you calculate that, I've swapped my V1s and my V2s in this case. So the first term is for that one, and you will get a minus 0.1 plus J 0.05 V, that is now V1. Then the second term for this one, that is going to give me plus 0.3 plus J 0.05 V2, and that all must equal the minus 8. Okay, and since I'm looking for V1, we can then write that V2 equals, and this is now a bit of a schlep. Now we need to take this term, needs to go over to the other side. This whole term needs to go over, and then we divide it by this one. So this is going to look as follows. It's going to be, if it goes over, this minus will become a plus, and that plus will become a minus. So it's going to be 0.1 minus J 0.05 V1 minus 8, this one that was there, and all of this now divide by this 0.3 plus J 0.05. Okay, and let's call this then, for argument's sake, equation number 3. Now, we're going to substitute 3 into number 1. That one ish. So all of this goes into that V2 so that we can solve for V1. Man, I'm out of space, so I'm not going to even do that. So now you do, if you put 3 in 1 that you've got there, what will you get? Then you will get V2. This whole block goes into that V2. This needs to get multiplied with that. You get your V1s together common, and you're going to get V1. I'm just going to give you the answer, the 11.76 angle 72.9 degrees volts. And you know what? As I'm doing this, I'm thinking by myself, now how exactly is this nodal analysis easier than the KVL and KCL that I did first? And now I know why I'd rather use KCL and KVL instead of this nodal analysis, because you still have a lot of complex algebra that you need to substitute to finish all of this. So yeah, that exercise that you need to do with complex calculations, yeah, that it still becomes hectic. Okay, but you must get to the same answer. So I'm going to leave this that number crunching up to you. I'm already going way over the time that I want to for this. That was just practice problem 10.9. So if you do get a dependent source in your circuit, yeah, it's going to take you time. The next one, I think we've got one more that I want to do. Yes, one more practice problem for this lecture, and then we're done. One more Thevenin and Norton. We're going to do a Norton for the next one. Okay, the last problem that we're going to do is practice problem 10.10, and my voice is getting tired and my feet's getting sore because I've been doing the whole chapter 10 in one session. You can listen it over 2 sessions. So here's our last circuit. 2 sources in there, a voltage and a current source. A weird branch crossing over them. Don't now look at this as a Y or a delta. We're not going to use that. So they want us to get the Norton equivalent now between terminals. Should probably call them A and B. And then once you have the Norton equivalent between these 2 terminals, that's your load. So Norton meaning we're only going to look at that part of the circuit. This is like your load connected to your circuit. And perhaps I should have mentioned this when we started with Thevenin and Norton. Remember, the whole purpose of a Thevenin or Norton equivalent is to simplify the complex circuit to just one source and one impedance, so that you can easily disconnect and connect different loads to that circuit and calculate what the load current or power or voltage is going to be. So for a big amplifier circuit, for example, you don't want the whole schematic. I just want to connect the speaker, and can I connect the speaker and what will the output be? So I want the equivalent circuit for all of this. All right, first let's find the Norton equivalent. What is that going to look like? For the sake of space, I'm just going to remove this for now, and we're going to look into these 2 terminals, but it's the impedance, Norton equivalent impedance, which is exactly the same as the Thevenin equivalent impedance. So let's zero our sources quickly. The current source disappears. I must just remember to put it back now. Now I wrote on wet board. Now it doesn't want to go away. And the voltage source is going to be, I made problems for myself, a short circuit. So this is what the circuit looks like for my equivalent impedance. Can you see it? How is all of this connected now? In series, parallel, because this whole thing is just one node. Let's make it like this. And this. All of that is just one node. And all of this is node B. So you've got node B there, node A on that side. So all of this is just parallel. And let me just get my answer there. So in other words, Z Norton is 4 + j2 + 2 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 + j2 parallel with, where's the dot? Let's add the two real components together. 9 minus J3. Okay, and that gives you then, not a beautiful number, but okay, 176 plus J 0.706 ohms. So much less effort if you don't have a dependent source in the circuit, isn't it? Okay, Norton impedance sorted. Okay, now I'm going to need the Norton current. So now I just need to put back all the stuff that I took out. So current source comes back, voltage source comes back. What were the values again? 4 angle minus 90, 4 angle minus 90 degrees, and amps. And the voltage was 20 angle 0. 20 angle 0 degrees volts. Now remember, for a Norton equivalent current, what we then do is we put a short circuit there. And I want to know what is the I short circuit, which is your Norton equivalent current. So we want to calculate that current. That's now without the load, remember? So our Norton current. So let's the short circuit current or Norton current. Okay, so I need to solve for a current. Man, this chalk is making so much dust. I'm going to probably get some illness when I'm turning 65 or something. Anyway, but the dust-free one doesn't want to write on this board. So yeah, what I wouldn't do for my students. Okay, so I need to solve for that current. If you want to solve for a current, nodal analysis, mesh analysis, well, remember currents, think Kirchhoff's current law, think nodal analysis, or, well, in this case, we've got a, what's that noise? Oh, it's contractors. What if we use, so if I want to use nodal analysis, I'll get the voltage there. Is that going to help you? Well, there's no impedance there, so I'm not going to get the current there. That's not going to help. What if we use mesh analysis? If I make that a mesh, and that a mesh, that a mesh, and I don't mesh it up, what's going to happen now? I've got two meshes, but there's a current source in the middle here. So this will actually have to become a super mesh that I've got there, and I've got that top mesh. But if I can solve for this, which way did I number it? 1, 2, 3. 1, 2, 3. If you solve for I3, you've got your Norton current. Okay, so I think let's go for the mesh analysis. This, I think, will be a good exercise. Okay, from the super mesh, so I'm going to write this over here, from the super mesh. Okay, and why do I know it's a super mesh? Because these two meshes share a current source. But from that, you can now write an equation. I3 minus I1. Can you see that angle there? So I3 minus I1 must give me that force. So I3 minus I1 must equal 4 angle minus 90 degrees amps. What am I looking for here? I3 is what I'm looking for. So which one do I now need to solve to get I3? I need to solve for I1. Yeah, mesh 1. Yeah. Now, let's see what happens when I write it out for mesh number 1. So voltage is high, so I'm coming in at the negative terminal of this 20. So it's minus 20. Plus, I'm going through, oh, the 8 ohms. Oh, there's the 8. What you're wondering. Plus 8, but I'm in mesh number 1 now, so it's I1, and flowing on top of that, it's minus I2. Okay. Then, that's through, it's a super mesh that you need to go through, silly. Mesh super. Then we're going to go through the 1 and the minus J3 plus the 1 minus J3. So what's flowing through that one? I'm now moving in this direction. Remember, I'm in my super mesh now. So it's in the same direction as I3, and going in the opposite direction is I2. Right, going through, that's it. That's the 2. So all of this must equal 0. Alright, I3. I want to solve for I1 in this. So there's an I1 and an I2. There's an I3 and an I2. Okay, let's keep this one for this here. That's the one equation. So remember, I've got 3 unknowns here. I can only write, well, there's one equation, there's a second equation. So we need to write a third equation because there's 3 unknowns. So let's go and write for mesh 2. So mesh number 2, that one. Let's start with the 4 plus J2. It's only multiplied with I2. Then we're going to move through the 1 minus J3. So plus 1 minus J3. And that now gets multiplied with I2 minus I3. Okay, because I2 is in this direction and I3 is in the opposite direction. And then I need to go through that 8 ohms plus 8. What currents are flowing through there? It's I2 minus I1 equals 0. So now I'm going to get all my I1s and I2s and I3s together. Put that there. So all the I1s, only that one, let me just write there. But it's a minus and a minus, that's a plus, silly. So it becomes minus 8 I1 plus. How many I2s? You're going to get 13 minus J1 I2. I just want to double check. 4, 5, 13 plus J2 minus 1J, nothing, minus 1J. Right, so that's fine. And then plus for the I3s, no I3, there's an I3. It's a minus there. So it's minus, no I3s there. So it's just the 1 minus here. But it's the minus. So it's minus 1 plus J3 I3. Okay. I'm going to call this equation, oh yeah, must equal 0. Sorry. Must equal 0. Make this equation number 3. I3 is the one that I want to be solving for. So I'm going to write this now in terms of I1 is, in other words, equal to, I1 goes over, so it's I3 minus 4 angle minus 90 degrees. I'm going to make this my equation 1. Now, where am I heading? I don't want to get rid of I3s because I3s, the Norton current, is the one that I'm looking for. So what's going to happen is, in this third equation, I'm going to plug equation 1 into this, and then, in other words, substitute this I1 with this expression for I3. In this equation, what I'm going to do is this I3, how did I write this one? Sorry. Yeah. I'm going to substitute this I1 with an I3. So let's put this I1 into that. So what do I then get then? I get minus 20 plus 8 times. And now, did I write that whole thing out? Oh, sorry guys, my brain is getting a bit tired after 2 hours. I3 minus 4 angle minus 90 degrees. Okay, so that's that I1 term minus I2 plus 1 minus J3. The I3 I3 minus I2 equals 0. So now in this equation, I only have I3s and I2s. I want to get something I2 equals something I3. Here I got I1 equals something I3. From this equation, I'm going to get I2 equals something I3. So that I can substitute that I1 equals and the I2 equals into this I1 and into this I2, and I get an expression only in terms of I3s, and then you solve. Okay, so this is now again through substitution. The other option that you of course have is the determinant method, 3 by 3. I can't remember how to do that. So, and my calculator usually does this for me. Your calculator can't. So I'm just going to use substitution. Okay. From this, let's get all the I3s and all the I2s together. So let's look for I2s. There's an I2 that gets multiplied by an 8. So, yeah, that gets multiplied by an 8, and there's, so it's a 9 minus J, 3, but it's a minus that I'm multiplying with. So it's minus 1 plus J3 minus 8. So it's minus 9 plus J3 I2. Let's see if I got it correct with my tired little brain. Yes, I did. Okay, plus all the I3s. 8 I3. 1, so it's 9 minus J3 I3 equals, now all the constants need to go to the other side, which is that 20 needs to go over, and this 8 times 4, which is a 32, so plus 32 angle minus 90 degrees equals, that gives you a, sorry, let me just write that a bit clearer. That equals a 20 minus J 32. Okay, but I still don't have I2 equals. So let's write this. So now this term would have to go over to the other side, and then we divide by this. So in other words, I2 must equal that 20 minus J 32, right? That term. This goes over to the other side, so it becomes minus 9 minus J3 I3. So now this term is over to the other side, and now I need to divide it by that term, minus 9 plus J3. Okay, so that's a bit of a doozy, eh? Oh, did I simplify this? Ugh, yeah, I did. Because this and this is so much the same, so I actually simplified it simplified it one more step into a 3.98 angle 140.4 degrees plus I3. Right, and this is then my equation number 2, that one. Okay, equation number 2. So next in the substitution process, man oh, and again for the sake of time, I think I'm not gonna write everything out because it's now just number crunching. Now you're going to take equation 1. You're going to take equation 1, substitute it into that I1. So you're going to get minus 8 times this. Then you're going to take I2, this part. You're going to plug it into I2 and multiply it by the 13 minus J1. And then you get equation everything in terms of I3. Something I3 plus something I3 plus something I3 must equal 0. And then you're going to solve for I3. So I'm going to write it over here. So in other words, 1 and 2 in 3. Let's see if I can't at least give you a tip. Yeah. So let me give you an intermediate step. You must ultimately, after all the substitutionals, get something of the form of a 4 plus J2 I3 must equal 37.547 angle minus 6.116 degrees, which then means that I3, or rather I Norton, equals I3 equals 8.396 angle minus 32.68 degrees amps. So now your head is probably going, sir, are you going to ask us something like this in the exam? Let's put it this way. What do I want to test in this course? I want to test your ability to solve circuits, to apply methods. Doing number crunching, for me, that's take time. So what I would rather, if I give you a complex or a sizable problem like this, I would typically ask, write for me the 3 mesh equations: super mesh, mesh 2, super mesh equation 1, mesh 2 or big mesh outer loop, and then mesh number 2. Write those equations. Then I would say, all right, now let's assume you get the results I1, I2, I3 is this. Now solve for me the I out. All right, so now I give you I1, I2, I3. So now you know your Norton current, you've calculated the Norton equivalent current, and now I ask for the B part, where the B part is with the load reconnected, which was how much? 10 capacitor. Yep, capacitor. 10 and a minus J5. Now, what does your Norton equivalent look like? Sorry, so the B part asks for, after you've calculated the Norton equivalent current, you must now calculate I out. So our Norton equivalent circuit now looks like this. A resistor, an inductor, terminals AB, and connected to that is, the 10 and the minus J5, and the Norton current there, the I3, is, hi guys, I can't even remember now if I gave you the final answer for the Norton current. No, I probably didn't. That's not nice of me. No, I did. There it is. So we know what I Norton is, right? It's that value. So how am I going to get I out? So I out is now your Norton current multiplied with, well, I want the current through the output impedance. I know what the Z Norton is. It's the 3.176. Sorry if you can't see lekker. And this is a J 0.706. So it's going to be Z Norton over Z Norton plus my Z, Werner, I'm thinking load, Z load. Where your Z load is the 10 over minus J5. So if you're going to write all of that out, which is, this is almost not going to fit on the page. Okay, but let's try. So it's going to be the 8.396 angle minus 32.68 degrees. It's not going to fit. Multiplied with, now we're going to write that part, 3.176 plus J 0.706. And if you add the load impedance to that impedance, the 3 and the 10 gives me a 13.176, and minus J5 and that one gives me a minus J 4.294. And then your final answer here for I out equals 1.97 angle minus 2.1 degrees amps. Okay, that's the last answer for today. So what was their objective is to calculate I out. They decided to calculate I out by converting this whole circuit into a Norton equivalent circuit. Norton impedance, quick and easy. Getting this Norton current required three equations, three simultaneous equations. That's a big pain in where you don't want a pain. So how would I, unless the question actually stated get the Norton equivalent, which this one now did, but let's say they just asked, listen, calculate that output current for me. You could have used nodal analysis, you could have used mesh analysis, almost like we did here, because now with mesh analysis with just, you still would have ended up with three equations though, but then with that load connected in source transformation, not a chance, because you don't have anything in series there or parallel. Source transformation wouldn't work. What about superpositioning? Getting rid, then, superpositioning would have perhaps worked very deliciously with this one, if you wanted to calculate the output current. Okay, but this problem is probably as hectic as it can get. So please go and I've cut out a lot of the calculations because it's important that you understand the methodology or the thinking, the number crunching that you can do on your own. So make sure you actually get to those answers. If you don't, go and look for your mistakes somewhere. Okay, because I've worked through these a couple of times. What else do I want to mention? No, that's it. Okay, I'm tired now. My feet hurts and my voice is croaking and I'm filled with chalk. So I will see you in the next lecture. We're going to start with chapter 11 in lecture number 16. All right, so I'll see you in the next one. Cheers. Bye-bye.